Hello, my name is Thomas. I'm the founder and CEO of Hyliion, and I'm here to talk about some staggering stats about electrification and also share with you a little bit about what Hyliion is up to, what we do as a company. So bear with me here as we start this off. I'm going to start off with a little story. So you'll see here, some pictures, and you probably think, well, hey, this is just like a snowy road. What's the significance of this? Well, this is actually a few years ago, and it's in Austin, Texas. These pictures were taken by our team down there, and you're probably thinking, like, how did Austin, Texas get an ice storm like this? How did you have bursted pipes? Well, climate's changing, things are evolving, and guess what? The grid was suffering during this time. Almost everyone lost electricity. There was about 250 deaths, unfortunately, during this time in the area. So, and grocery stores were totally picked over. So, the reason I bring this up is because we're bringing forward a solution, a technology that's really focused on addressing this problem, enabling distributed power generation. A lot of this show is focused on wind and solar. We're actually focused on a generator that can provide prime power application, really like a mini power plant. So this is a solution we are bringing to market as a company. The box that you see here on the slide is a 200 kilowatt generator. Now this is our base model. You can expand this up to a few megawatts of power as well. But the goal of this is to really enable taking a microgrid and actually having a genset within that microgrid that can be sitting there running, providing electricity. So I'll start off, we're going into details on how the genset works. Start off with some of these staggering stats about the US electric grid. So the first is that it's recent reports that just came out is that the expected growth of the demand need for electricity has actually doubled by 2028. So reason for that is, as you think about the utility in the past, you kind of have the commercial applications, residential applications. We now have new things coming online. Data centers with AI, skyrocketing, industrial sector, there's this push to move to electric, hydrogen production, much of it uses electricity, and then EV chargers. As we get more EVs on the road, obviously that's putting a toll on the grid. So this is the data that actually, possibly, there we go. That I was talking about it was expected in 22, it was expected that by 2028, we would see 2.6% growth of demand on the electric grid. The recent report that came out last year is actually saying that it's going to grow by 4.7%. So that's a major change. It means that we're going to need more electric production than we previously thought. So the next stat, talked about EV chargers being one of the main drivers for more electricity need, is if you plug in 10 BEV semi-trucks, that's going to consume as much power as the entire Super Bowl stadium during game time. So 10 semi-trucks is nothing, right? I mean, that's a drop in the bucket. There's a couple million semi-trucks out there on the road that we're trying to push to move into electric. So the goal is that when these trucks plug in, they're going to be pulling about a megawatt of power. And if you take 10 of those, that's going to be equivalent to 8,000 households, or about 10 large hospitals, or one Super Bowl stadium. The next stat is the electric grid over the last 50 years has only shifted 3% towards renewables. So as you think about renewables, wind and solar, it's like you think, oh wow, there's been so much movement over the past few decades. Well, the reality is that's only had a 3% shift in where our electricity is coming from. So here's the graphics from 1971. You can see we were using a lot of coal, right? 14%, and then, that's petroleum. Then coal was the 44%. So we've seen a big reduction in petroleum, big reduction in coal. But the reality is that renewable bucket has only grown 3%, and that's the green bucket. So as you think about the difference of bringing on more wind and solar versus actually bringing on generator technology, one of the things you got to consider is the duck curve, right? Which means basically It's sunny during the day, it's not sunny at night, right? So this is our argument of why you actually need a generator as opposed to just putting more renewables onto the grid. So this is data from California. You can see that in 2023, by midday, basically, when the sun is shining, that's providing the power needed for the grid. But obviously in the early morning, late afternoon, when people are really tapping into using electricity, that's when we don't see any production from solar. So another fun solar stat here is, there's a famous quote out there of Elon Musk saying, well, why don't we just put solar panels out there? All you need is 100 miles by 100 miles of land, and that would power the entire US. You would obviously need to couple that with batteries as well, just due to that duck curve I just mentioned. But let's look at that. I mean, that 100 miles by 100 miles is about the size of Vermont. If you compare that to if you actually just use power generation technology as opposed to solar, you're looking at a much smaller footprint. So that white dot is about the size of land you would need to power the entire US off of these KARNO generators. So obviously a much smaller footprint than what you would need out of solar. So fact number 4 is, most people don't realize this, but the US electrical grid is only 36% efficient. So if you think about different power generation technologies, up in the top right, you can see that purple bar there. That's like the latest and greatest power plants that are coming out, the efficiency levels that they're producing. It is around 50% electrical efficiency, but the reality is our US electric grid is not at that point. Our US grid is at more that 36% efficient, that blue line that goes across. So what we envision is, well, what if you could actually have microgrids that have that same efficiency as what these brand new, latest and greatest power plants have, but you don't need the hundreds of acres to deploy a plant. You could actually have a generator that sits out back of a facility producing at near power plant level efficiencies. All right, and then the last stat is microgrids can be 2.5 times more affordable than the US electric grid. So I actually took this data from my parents' house in Massachusetts. So this is a state that electricity does cost a lot. So they're paying about 31 cents per kilowatt hour at their house right now. And if you look at the natural gas pipeline that's coming in, they're able to buy natural gas at $1.57 per therm. So we took this information, we looked at, well, what if you ran that through a KARNO generator that we're producing? What's the actual cost of a kilowatt hour of electricity? And it comes out to about 12 cents per kilowatt hour. So even at like a small residential type of an application, you actually have the ability to be producing electricity locally for cheaper than what you can source it from the grid. All right, so to recap, there's growing demand for more electricity need. I don't think anyone's arguing that, and it's even going faster and faster than initially expected. We need cleaner generation solutions, and our thought is you need more efficient generation solutions, right? If you can move that US grid from being 36% efficient up closer to that 50% efficiency, that means you can start using less fuel and be producing even more power. And then obviously the end customer's whole drive is let's lower the cost of electricity while we're at it as well. So now we'll dive into, those are kind of the fun stats. Hopefully some of them you take away and you use them as you're talking to people. I mean, the one that I've always found stands out is that, 10 semi-trucks consumes the same power as the Super Bowl. That usually is pretty eye-opening for people. But I want to spend a few minutes now shifting and talking about the actual solution that we're bringing to market, how it works, and how we're enabling, everything I just mentioned. So we've got a generator solution that is based off of Stirling engine technology. So Stirling engines aren't new. They've been around for about a century. Even in the 80s or so, NASA did a bunch of work on Stirling heat generators. But there was always an inability to really get to the efficiencies needed. And I'll talk about how we've been able to unlock that here in a few slides. But this is the benefits that this generator is bringing forward. So it's fuel agnostic. It can run on over 20 different fuels. So whether it's hydrogen, natural gas, propane, diesel, ammonia, the list goes on, but a truly fuel agnostic platform. One of the questions we often get is, can you really switch from one fuel to the other? And the answer is yes, and you can do that on the fly. Not even needing to turn the genset off, you can actually change what fuel is going into it, and it's able to continuously produce electricity. Ultra low emissions, I'll talk about how we do this, but we use a process called flameless oxidation, which is an extremely clean burn of the fuel, and that allows us to get that low emissions numbers, as well as a long burn cycle. Very different than what an internal combustion engine normally sees. And then the high efficiency, this is really the unlock we had on Stirling engine technology. We're able to do this with additive manufacturing. So as you look at that picture on the right hand side, that's one of the shafts of the generator. Those parts you see are actually printed, 3D metal printed, and that allows us to make unique geometries, unique heat exchangers that unlocks efficiencies that never would have been able to have been achieved before. Minimal maintenance, so I'll go into this in another slide, but within that system there's only one moving part, and that part even rides on air bearings, so it's designed to have extremely low maintenance. There's no oils, there's no lubricants in the system, which also enables that long lifespan. And then the low noise, so at about 6 feet we're at about 67 decibels, so much quieter than a reciprocating engine is. All right, so now let's dive into how this thing actually works. So I showed on the last slide a picture of those shafts. Well, this is a 4-shaft setup. This system right here would produce 200 kilowatts of electricity, so each shaft about 50 kilowatts. So when you dive into it and start pulling apart the system, on the ends is where we do the reaction of the fuel. So we bring the fuel in, mix that with air, and do this process called flameless oxidation. Very similar technology to what's used in jet engines as to how you react the fuel. And then the whole goal of that process is to produce heat. So that's one of the unique things with a Stirling engine is the fuel source is not fuel, the fuel is actually heat. And so all we need to do is provide this generator with heat, and that's how we produce electricity. Now, we get our heat by reacting fuel. So you do that process, and then the whole goal of that is you're heating up a working gas. So in that area that just turned red there, that's helium, and the goal is you react the fuel, you produce heat, and then you heat up that trapped helium. Now when you heat up a gas, what happens is gas starts to expand, right? Now as that gas is expanding, that's what actually pushes on that piston and moves it to the other side. Now, the goal is this process is happening at a fast pace, right? So you have reactions happening on either side, and that piston is oscillating back and forth. And then in the middle is where we have an electric motor, so basically magnets, coils, that's actually producing electricity. So the goal from our end is these shafts are sitting there, that one part is oscillating back and forth, and it's producing DC power output. Now, we can take that DC power, convert it into AC, do a grid interconnect, or for applications like EV charging where you need DC power anyways to be able to power that vehicle, you can go direct DC to the end use case. So I mentioned this a little bit earlier, but the unlock, I mentioned Stirling engines, they're not new, they've been around for over a century. Well, the unlock is we're using additive manufacturing to make the key components of the generator. So kind of another fun fact here is, if you look at like heat exchangers on average, they're like 60% efficient, conventional heat exchangers. If you read textbooks, it'll say, hey, the max efficiency you could ever get out of a heat exchanger is around 80 or in the 80s. When we're using additive manufacturing to make these heat exchangers, we're actually in the 90s in terms of efficiency. So a 90% efficient heat exchanger is unheard of, right? But that's the unique thing with additive manufacturing is you're no longer constrained to how do you, mill a part or how do you CNC machine it. Now you can create geometries that could never have been made before. And you can see an example of what one of the heat exchanger parts looks like on the left-hand side of the slide. And then on the right-hand side, this is actually a picture of what additive manufacturing equipment looks like. So the left-hand side is the unit that I had shared on the very beginning, a 200 kilowatt box. That's a unit that we're starting to ship out to customers later this year. In the center is kind of the larger platform, so a 20-foot shipping container size box will be at about 2 megawatts of power output. And then long term, we actually see opportunities to even go to a smaller footprint. And you think about more of like a household application. It enable, a smaller 10 to 25 kilowatt solution would enable localized power generation right at a house. And then this is just a fun closing slide. So I mentioned one of the markets we're going after is the EV charging market. So you can see a look at kind of what we see deployments looking like, where you're going to have EV charging pedestals, and then you would actually put the generator right next to it, producing the power needed. Now, in these applications, one of the other unique unlocks is the EV charging industry wants to be clean, renewable, right? Hydrogen has often been the fuel spoken about of kind of the fuel of choice for that industry. The reality is they can't get access to the hydrogen today, but with the KARNO generator, you actually open up this ability to where you could deploy today on natural gas, but future-proof yourself to, if and when hydrogen does become available, that same technology you've deployed also has the ability to run on different fuels. So with that, we'll open it up to any questions that anyone has. Yeah.
How hot do your generators get?
Yeah, so it's actually a very, in the world of reaction of fuels, it's actually a very low temperature reaction. So from the outside that box, I mean, safe to touch. And then from an exhaust gas standpoint, much lower than what a reciprocating diesel engine or CNG engine would be. So what we're actually doing is we try to keep all the heat inside those shafts, inside the cylinders. That's one of the benefits of those heat exchangers I showed is we even take like exhaust gas and we preheat the inlet gas coming in so that we don't lose that efficiency.
Hi, how are you considering your technology for marine auxiliary engines, which are producing electricity for the ship?
Yeah. So we are. The question was around, are we considering the marine industry application? And we are. We actually are already underway on a project on that end. So the 4 buckets we're going after first are EV charging, the ability to use waste gas. So if you think about like gas coming off of landfills, dairy farms, where normally you would need to scrub that gas before using it. You don't necessarily need to do that with the KARNO generator because of the fuel agnostic capability. So that market, prime power, so like warehouses, facilities, and then the 4th one is the marine application. And we've actually already done testing on taking contaminated diesel fuel, so diesel fuel that's been contaminated with like salt water, and the genset can work just fine on that.
You mentioned that the technology is fuel agnostic. For what fuel is it optimized?
Yeah, so it really sees similar efficiencies regardless of the fuel you're running on, because the only thing we're using the fuel for is to make heat, right? So you'll see around that 50% electrical efficiency, whether you're running on natural gas, running on hydrogen, running on propane. So now, full transparency, most of the customers we're working with, they want to run it on natural gas to start, right? They like the idea of the hydrogen story in the future, but most of our testing development has been done on natural gas, but it's not necessarily optimized for natural gas. It's kind of optimized for all the fuels just because our only use of the fuel is to make heat. Yeah, another question.
You talked about efficiency with the new use of fuel and making heat. Can you tell us a little bit more about efficiency? And the reason I ask is an internal combustion engine using gasoline maybe 28% efficient. Sure. I'm not exactly sure. How do you measure efficiency and also exhausting GHG? Are you doing it in terms of efficiency?
Yep. Yeah. So Couple of different things to peel back there. So efficiency of the generator, everyone has a different way of expressing efficiency, right? It's like the most complicated thing to try to understand how someone's expressing it. So our thermal efficiency of the genset is around 59% thermal efficiency. Our electrical output efficiency, so fuel in to actual electron out, is that 50% that I've been referencing through the presentation. That'll be at DC power out. Now, if you need to convert that into AC power, you would see a couple of percentage drop of efficiency just going through that conversion. One of the other unique things with this is you talked about the ICE engine efficiency. Depending on the power level, it has very different efficiency levels. Even to use fuel cell for an example, like fuel cells will claim in the 50% efficient range. That's usually around like 65-70% power output. If you bring a fuel cell to 100% power output, it's basically fallen off a cliff and the efficiency is a lot less. With the KARNO generator, we're going to hover right around that 50% electrical efficiency, anywhere from 50% power output up to 100% power output. So that's another pretty unique advantage is you don't have to stay right at a sweet spot of power output to get that efficiency. We've got a pretty linear, flat efficiency sitting at that 50%. Then in terms of GHG, you were asking, so if you bring a fuel in like natural gas that is going to produce CO2 emissions, your efficiency, your emissions improvements is really going to be driven by the reduction in fuel usage. However, if you look at NOx and CO emissions, since we have that long flameless oxidation process, it's a much longer burn, cleaner burn of the fuel, our NOx levels and our CO levels will drop in the north and 95% lower than what an internal combustion engine's NOx and CO levels are. And so as you look at like CARB's emission standards on the NOx end, we will not need any after treatment system to be able to meet those on natural gas. Yeah.
Just a follow-up question. In a marine application, you would have a main engine.
Yes.
Is the exhaust gas at all suitable to create either the heat or to supply the fuel for the engine? Or is it
yeah, so we need higher heat levels than what like an exhaust out of another engine would be. You could use that to improve your efficiency, so you could kind of preheat the inlet gas out of the exhaust of another engine. And then going back to your earlier question, we have both looked at using the KARNO generator as kind of the APU load for a ship, but also actually using it as the prime power mover of the ship as well.
At that 12 cents a kilowatt, is that fully loaded or is that just operation?
Yeah, that was fully loaded LCOE cost.
Can you speak to the ramping capabilities of the unit?
Yeah, so since our fuel source is heat, if you're starting from cold, it does take a little while to come up. So about 30 seconds ballpark until we can produce positive power output, and then about 3 minutes till we're at full power, 3 to 4 minutes till we're at full power output. So that is one of the disadvantages. If you take a diesel engine, it's like 10 seconds, you're up and running at full power. If you take a fuel cell, like a solid oxide one, you're 30 to 60 minutes until you're at full power, right? So we're closer to a reciprocating engine in terms of the bring up time, but we are slower. So we don't really see this as like a standby power application though, right? Because honestly, if you're looking for just backup power, just go buy the cheapest engine you can find or least expensive, and not saying cheap because of quality, just like least expensive engine. This is more designed to be that prime power. So the other aspect is how fast can we respond to transients, and we are very much in the equivalent ballpark of what a reciprocating engine can do from a transient response standpoint. But we do take a little longer to come up to speed or come up to heat in the beginning. Yeah. Any other questions, or we got a minute left, so. All right. Oh, one other one.
Could you speak to the reliability and the availability of the machine?
Yeah, so reliability, that shaft moving back and forth, the piston setup, it rides on air bearings. And as I mentioned before, there's no oils, no lubricants. So we're looking at, there are some parts that over time will need to be replaced just due to like heat creep. But it's years of runtime before needing to be worried about that, and even we're targeting north of 10 years before you would need to do any like sort of major overhaul of the system. So so pretty long life, and then availability of the system. We are just moving into production starting later this year and shipping out to customers. So this is a technology, quick background, I know we're running out of time, but it was initially invented within GE. Hyliion then acquired it out of GE a couple of years ago, and we've been bringing it to market, and that starts later this year. Great, thank you very much, appreciate it.